Okay, here we are at our lesson for engineering and scientific notation. And in this lesson we have a few objectives. First is to understand the difference between engineering and scientific notation, to be able to convert a decimal number to engineering notation, and to be able to convert a decimal number to scientific notation. So let's get started. And we're going to start with engineering notation first. This is used quite commonly in the electrical field, and that's why we're studying it. So we have some rules that we need to follow for converting a decimal to an engineering notated number. First is numbers that are between 1 and 999 are left alone. They're stated as such. There's no suffix on those. But numbers that are represented in engineering notation must contain at least one whole number to a maximum of 3 whole numbers to the left of the decimal point. So we're talking about a number that is going to be larger than 999 or smaller than 1. Okay? Those are numbers that we are going to notate in engineering notation. So that's very important to realize that. And numbers represented in engineering notation are going to be rounded off to the third decimal place after the decimal point, or to the right of the decimal point. And we're going to look at that here in just a moment. So here are our engineering notation quantities. Okay, we'll start moving in the positive direction. The first number larger than 999 is 1,000. And anything that is from 1,000 up to 999,999 will have a K behind it for kilo. Okay, and that's probably the most common. You've heard of kilometers, you've heard of kilograms. Running a 5K as far as distances. That's probably the most common one you've heard of. Okay, so K is going to represent kilo, and that is going to be representing in the thousands of magnitude, okay? And that is represented by 10 to the third power. But we have some others here. If you get up to 1,000,000, that's going to be mega. So anything from 1,000,000 up to 999,999,999 will have this mega behind it. Get 1 over that, you're going to be into the giga range. And the giga range is going to be a 1 with 9 zeros behind it, and is represented 10 to the power of 9. Okay. Now I also stated that we're going to be representing numbers larger than 999 or less than 1. So the first denomination that we're going to talk about here is the milli. And if we move the decimal point over 3 places, notice that everything that I'm doing here is at quantities of 3. Okay, so when we're going in the positive direction here, it was 10 to the third, 10 to the sixth, or 10 to the ninth. When I'm going in the opposite direction here, numbers smaller than 1, I'm going 10 to the negative third, 10 to the negative sixth, 10 to the negative 9, and in the case of pico, 10 to the negative 12. Okay. So if we get numbers that are between 1 and 1,000th is what that actually represents, we're going to use the symbol milli here. Okay. If we go 6 more places, we're going to get 10 to the negative 6. We're going to use the term micro. This is the letter that's going to represent micro for us. We use that a lot in electrical terms. Milli here will be for milliamps. Amps less than 1 amp will be denoted as milliamps. Micro, we could have microfarads for a capacitor. We'll get into all those different units. But a farad is can be a rather large unit, but a capacitor can be very small in that regard, and we can use this micro term. Nano, you might have heard that for just denoting something that's very, very small. And you can see the size here, 10 to the negative 9, and that is represented by the letter N for nano, and pico. There again, capacitors can get as small as they can be in the picofarad range. We'll talk about that in the future. But that is represented by 10 to the negative 12, or there are 11 zeros in front of the 1 and then the decimal point here. Okay, so let's do some conversions and see if that will solidify these noted quantities for us. So let's convert this number to engineering notation. Okay, now we have more than 3 whole numbers to the left of the decimal point, so we need to resolve that. So that's the first thing we're going to do, is we're going to see if we can get it down to 1, 2, or 3 numbers to the left of the decimal point. So I'm going to move this over 3 positions to the left. Okay, and if I'm moving to the left, that means I'm going to be going in that larger magnitude. One thing I didn't state here is, if you notice, when I go in this positive magnitude here, these are capital letters, K, M, and G. When I go in the smaller direction, they are lowercase m, micro, nano, and pico. Okay. So here I am going to be moving the decimal to the left 3 positions. Okay, so I'm going to be needing to multiply, basically, or use a quantity that would be the same as increasing the number. So this is going to be kilos, and I'm going to use the capital letter. And in doing so, I have 3 whole numbers now to the left of the decimal point. So let's look at that. So now I moved my decimal point from between the 4 and the 8 here. I moved it over 1, 2, 3 positions to right there. So now I have 139, or 139, in front of the decimal point, and then the remainder of the digits are to the right of the decimal point. Now we said the other rule is we want to trim those extra digits to the right of the decimal point, and we need to round if necessary. Okay, so we want to go 3 digits to the right of the decimal point, and because this has an 8 as the 4th digit, we are going to round up. Okay. Add the suffix for kilo, since we moved to 3 positions to the left, and here is my rounded number and my letter K behind it, and that is an engineering notated number that represents this number right here, this decimal number right here. Okay. So that's looking at it in going into a larger magnitude. Let's look at going into a smaller magnitude. So we're going to convert this number to engineering notation, and we're going to need to move the decimal point in the other direction. Okay. So here we're going to move the decimal point to the right 3 positions to represent milli. Okay. 3 positions, moving 3 positions to the right will be milli. So here I took the decimal point and I moved it 1, 2, 3. So I'm going to be right behind my 2 and my 8. In doing so, I have 1 whole number to the left of the decimal point. That satisfies I need to have 1 to 3 digits to the left of my decimal point, and I have 1 to the left of my decimal point, so that satisfies that rule. And this is the number that is represented in doing when I move that over 3 points. Okay, 3 positions. So 2.899271. But I need to trim those extra digits, and I need to round if necessary. So I have 899, but it's followed by a 2, and since that 4th digit is less than 5, okay, so 0 through 4, I will not round up. Okay, I'll just trim those off. So I get 2.899, and we said earlier that it was going to be milli. So I need to add that suffix on there because I moved 3 positions to the right, and that is my engineering notated number that represents this decimal number here. So that would be pronounced 2.899 milli. Okay. Let's take a look at scientific notation now. It's a little bit different. The rules are a little bit different, so let's look at those. only one whole number shall be to the left of the decimal point. Okay, that is the first rule. It's much simpler. You only have one whole number. Okay, it's not the 1 to 3 like we do in engineering notation. Just one whole number to the left of the decimal point. The remaining digits shall be to the right of the decimal point, and in our case, in this class, we are going to round to 3 decimal places. Not everywhere that scientific notated numbers are represented are rounded to 3 decimal places. We're just going to do it for our purposes here. The number's value shall be multiplied by 10 to the necessary power to gain the equivalent value of the decimal number that we started with. Okay, so let's do some conversions here. We're going to convert this same number that we did for engineering notation, but we're going to do it to scientific notation. So the first thing that I need to do is I need to move that decimal point over to here. Okay, so I need to move that decimal point over 5 positions. So let's look at that. We're going to go 1, 2, 3, 4, 5. So it's 5 positions to get one whole number to the left of my decimal point. Okay. So that is what we're left with, and we have a whole bunch of digits to the right now. We said that we were going to round to the 3 digits to the right of the decimal point, so we'll do that here. And since my 4th digit is a 6, we need to round up. Okay. So we're going to round those to the 3 places, and like I said, because we have 6 at our 4th position, we need to round that 5 up to a 6. And now we need to multiply. We moved 5 positions to the left, so we need to multiply by 10 to the 5th. Okay, the other way to think of that is 10, a 1 with 5 zeros behind it. Okay, so if we multiply this by our 10 to the 5th power, that is a scientific notated number rounded to 3 digits that represents this decimal number right here. Okay, let's look at another one. This is the going in the opposite direction, and it's the same example that we had in engineering notation, but we're going to use it for scientific notation now. Okay, so we need to move 3 positions to the right to get that single digit to the left of the decimal point. So here I took the decimal point and I moved it over 1, 2, 3. Okay, so now we are going to have that as our representation. But again, we need to trim this to 3 places to the right of the decimal point. So those remaining digits will be rounded to 3 places to the right. And since this is a 2 in the 4th position, we are not going to round up. And so we just truncate these 3 numbers off of the end. We're given that. And now we have to multiply by our factor of 10 to get back to our original decimal number. But we moved the decimal point to the right. And in doing so, we have to multiply by a negative number to move it back to the left. Okay, so here we are going to be using a negative power, or 10 to the negative 3, because we moved 3 positions to the right. And that is our scientific notated number that represents this decimal number, and our scientific notated number is rounded to 3 decimal places. Okay. Let's look at rounding in scientific notation. This is it's a concept I think sometimes it's hard for students to grasp, but hopefully this will clear it up. So we have another small number here that we need to convert to scientific notation. So we're going to move that decimal point over 3 places to the right. So we only have that 3 to the left of the decimal point, and that gives us that number there. And then the remaining digits need to be rounded. But look here, we have a 7, 9, 9, and then 8. Well, 8 means that we're going to have to round up. But if we round this up, that is going to put a 0 in that place. And it's going to carry over to this place. We're going to have a 0 there. And then it is going to round that number up there. Okay? So the proper way to actually denote that is we're rounding, in essence, 799 up to 800 here. Okay? And we want to show those trailing zeros there. That means something very different than just 3.8 times 10 to the negative third. Okay? 3.800 is more specific. Okay? So we are going to again multiply by 10 to the negative third because we move 3 places to the right. Okay? And that would be my scientific notated number that represents this decimal number here. And to be accurate, I need to carry out to the amount of decimal places that we had rounded to. Okay? A lot of people might think, well, if I actually multiply this out, I'm going to get the same number as I would if I didn't have those trailing zeros. And in one regard, that is accurate. But what this denotes to, especially a scientist, is how far out your accuracy goes. That's probably the best way to state that. Okay, let's review. Understanding the difference between scientific notation and engineering notation. Okay, so what is the difference between the two? Well, if we have a number 123.456 giga, that's going to be the same as 1.235 times 10 to the 11th power in scientific notation. So a couple differences that we note. Number one, we don't have this multiplication factor behind our engineering notated numbers. Engineering notated numbers are going to be bound by moving the decimal point in one direction or the other in groupings of 3, because that's what our letters are going to represent. Scientific notation, we don't have that boundary. So this could be 10 to any power here, and we can move the decimal point over in any number of steps to get one whole number to the left of the decimal point. And scientific notation, we're always going to have just one digit to the left of the decimal point, and in engineering notation, we can have 1 to 3 digits to the left of the decimal point. Okay. In both cases, the way I'm teaching it in this lesson, we are going to have 3 decimal points to the right, 3 decimals to the right of the decimal point. Okay. So in reviewing, we should be able to now convert a decimal number to engineering notation. So if we take a number like, let's see, that would be 45,712.34. If we converted that, that would be the same as 45.712 kilo. Okay. You see that I moved the decimal point over 3 positions there. That's why I used kilo. And I did not actually have to, well, I guess I did. I did have to truncate off some numbers there to get to my 712. Now we should be able to convert a decimal number to scientific notation. So if we take that same number, we need to move the decimal point over 1, 2, 3, 4. Okay, that's why we have 10 to the 4. And then we truncated off the 34. We didn't round up because 3 is less than 5, and it has to be 5 or higher for me to be able to round up. So I have 4.571 times 10 to the 4th. Okay. Hope that clears things up for you, and we will be using engineering and scientific notation as we move forward in our study of electricity. So we'll see you in future lessons.